This is our last lesson in geometric vectors, and today we're going to use our knowledge of vectors to unlock a skill that pilots, ship captains, and even astronauts depend on every single day: how to navigate the world when motion happens in more than one direction at the same time. So, when an airplane flies, it's not just moving forward through the air, it's also being pushed by the wind. If the pilot doesn't adjust for the wind, they could miss their destination. So, today we're going to use vectors to solve velocity problems, specifically with some airplane examples, and think about and calculate relative velocity. So, let's get started with an example. Okay, let's take a look at a question that uses velocity as a vector. So, we have a plane that's steering north 50 degrees east with an airspeed of 310 kilometers an hour. The wind is blowing from the north at 54 kilometers an hour. Find the ground velocity of the plane. What this is really asking us is to find the velocity as it would appear, the velocity of the airplane as it would appear from someone watching the plane from the ground. And to find that ground speed or ground velocity, we want to take whatever the actual airspeed of the airplane is minus whatever the velocity of the wind happens to be, plus whatever the velocity of the wind happens to be doing to it. Now, remember, the velocity of the wind, or think about it this way, the velocity of the wind can either push the plane along or slow it down in the air. And what that would look like from the ground. If you've ever ridden your bike or tried to canoe into the wind or run into the wind, you know that you have to increase your effort in order to maintain the same speed if you're running into the wind. If the wind is behind you, you don't have to work quite so hard. The same thing is happening to an airplane. So let's take a look and let's see if we can figure this out. This really is just a vector question. So we're going to tackle this the same way we've tackled all the other ones. We're going to draw a compass rose. We're going to add the vectors that we know by connecting them tip to tail. In this case, we know the airspeed is 310 kilometers an hour, and it's going north 50 degrees east. So let's add that in there. So here's my compass rose. Here's my north. Here's my east. And so if we go 50 degrees to the east, here is my vector for the airspeed of my airplane, and this is relative to the air. So the velocity of the airplane relative to the air is 310 kilometers per hour. Now, the wind is blowing from the north at 54 kilometers an hour. So what that means is it's coming from the north and blowing towards the south. So this wind vector is going to be heading straight south at 54 kilometers per hour. This is the velocity of the wind. Now remember, I said the ground speed, which is what we're being asked to find, is going to be the resultant of these two vectors, the velocity of the airplane relative to the air and the velocity of the wind as it's affecting the airplane. So if we were to add in our resultant vector there, this will be the velocity of the aircraft relative to the ground. This is just a triangle problem. In fact, we can go ahead and we can figure this out. Remember, we're going to find both the magnitude and the direction. We're going to find the magnitude using our cosine law, because using our law of triangles, we know that if this angle is 50 degrees, then this angle is also 50 degrees. So I have two sides in an enclosed angle. I can go ahead and get my magnitude using my sine law. Magnitude. So my ground velocity squared will be equal to 310 squared plus 54 squared minus 2 times 310 times 54, and that's cosine of 50 degrees. So my velocity of the aircraft relative to the ground, when we do all those calculations, will be 278.4 kilometers per hour. Now this is a vector, so we need both magnitude and direction. So we're going to find this angle right here and then add it to our 50 degrees. And I'm just going to put that up here. To find the direction, we can use the sine law. So I have sine of my unknown angle all over 54 is equal to a sine that I know. Well, I know sine 50, and the side opposite sine 50 is 278.4. That gives me an angle of 8.54 degrees. Now, that's the angle that's right here, but we already have 50 degrees, so we need to add 50 degrees to this, which gives us a total angle of 58.54 degrees from north heading towards the east. So, to wrap this all up and make our summary statement, the ground velocity, or the velocity of the plane relative to the ground, is 278 kilometers per hour, and that is north 59 degrees east. Let's look at another airplane question. So a plane is heading for a destination that's 900 kilometers away in a direction of south 20 degrees east. The plane wishes to reach its destination in 2 hours. If the wind is from the north 40 degrees west at 55 kilometers an hour, find the air velocity. So let's think about what information we've been given in this question. So a plane is heading to a destination 900 kilometers away in a direction of south 20 degrees east. That is the ground velocity, or that's our ground distance. And we also know the amount of time. So if we have 900 kilometers on the ground in 2 hours, then the velocity will be our distance over our time. So our velocity is equal to 900 kilometers divided by 2 hours. So the velocity relative to the ground of the airplane is 450 kilometers per hour. So this is the speed on the ground. This is the speed of the plane if you were standing on the ground and looking up at it. Now, remember that I said to you that the velocity on the ground is equal to the velocity of the aircraft relative to the air plus the velocity of the wind. The wind is relative to the ground if we really want to think of it in physics terms. So if I have my ground speed, so the speed that a plane appears to be traveling by an observer on the ground, is equal to the airspeed. That's the speed that the airspeed indicator, kind of like a speedometer, but for an airplane, inside the plane shows the pilot that it's going, plus the wind speed. And this wind speed can have a positive or negative effect depending on its direction relative to the direction of the plane. So if we know the ground speed, which is what we do have right here, we want to find the airspeed, then the velocity of the aircraft relative to the air will be equal to the ground speed minus whatever the wind happens to be doing. So we can tackle this by adding the vectors tip to tail and remembering to actually subtract the wind vector by reversing its direction. Or we can break the ground speed and the wind into its x and y components, subtract them, and then put them back together to get that airspeed, the velocity in the air. I'm going to use the component vector method for this question, but if you choose to do it the other way, you should get the same answer. So let's draw out what we have. I'm just going to move this up here a little bit. So let's start with the ground speed. So here's our ground speed. This is our VG. And I have a ground speed. We know the direction. We know that it is heading. We know that it's heading south 20 degrees east. So south 20 degrees east, and it has a magnitude of 450 kilometers per hour. I can break this into its x and y components. Here's my y component, my velocity of the ground speed, my velocity of the ground relative to the plane and in the y direction. And here's my ground speed in the x direction. In the x direction, it is 450 sine 20 degrees, which gives me 153.91 heading directly east. And my velocity of the ground speed, or the ground speed in the y direction, is equal to 450 cosine of 20 degrees, which is equal to 422.86 kilometers per hour, and that is south. Now let's do the same thing for the wind. So now we have the wind speed, or our VW. So same idea. The wind is coming from the northwest, so north 40 degrees west, which means that it is actually blowing through this direction, but we're not going to worry about that for right now. We're going to think about what this one is doing up here, and I'm going to draw it a little bit bigger. Okay, so here's our wind. So it is coming in this direction. We know that this angle here is 40 degrees. We know that its magnitude is 55. So now we need to determine our component vectors in the x and y direction. Our velocity of the wind in the x direction will be equal to 55 sine 40, which is equal to 35.35 kilometers per hour, acting in the east direction. And my velocity of the wind in the y direction will be equal to 55 cos 40, which is equal to 42.13 kilometers per hour. And that is south. Now, this is where we have to think about this a little bit. My velocity, the wind is going with the airplane. So it is going to make it appear faster on the ground. We want to know the airspeed. So this is where we are going to use this idea that our airspeed will be equal to our ground speed minus our wind speed. Okay, so our velocity or our airspeed in the y direction is going to be equal to our velocity, ground speed in the y direction, so 422.86, minus my velocity in the y direction for the wind, because it's pushing it. It's going to make it appear to go faster. 35 point... Oh, wrong one. In the y direction is 42.13. That gives me a velocity in the y direction of 380.73 kilometers per hour south. We're going to repeat that for the airspeed in the x direction. We have 153.91 east. Minus this time our 35.35. And that gives me a velocity in the x direction of 118.56 kilometers per hour, and that is east. So now we're going to put those two vectors back together and find our resultant vector. And I'm just going to give us a new page here, and we're going to do it on a second page. Okay, so we're going to put these two together. So I have 380.73 acting in the south direction, kilometers per hour in the south direction. And then we have a component acting 118.56 kilometers per hour in the easterly direction. We are wanting to find our relative velocity of the air, and we can do that. We can find the magnitude of it using the Pythagorean theorem. So VA squared is equal to 380.73 squared plus 118.56 squared. So our airspeed works out to be 398.76 kilometers per hour. Now we need to know, so that's the magnitude. Now we need to know the direction, and we want to know this angle right here. We can use tan to figure that out. So tan theta will be equal to our opposite over the adjacent, so 118.56 all over 380.73. So our angle equals approximately 17.3 degrees. So the plane's airspeed, when we put it all together, is, we're going to say 399 kilometers per hour, and that is at a heading of south 17 degrees east. So you've heard me talk a little bit about how the ground speed and the air speed are relative to each other. If I'm an observer standing on the ground, the airplane appears to be moving at a certain speed. If I'm in the airplane and observing in the other direction, the ground seems to be moving relative to the airplane in the opposite direction. And that's what we're going to talk about right now, is this idea of relative velocity. And relative velocity really is just how fast something is moving compared to something else. It answers the question, how fast does it look like the object is moving from the point of view of another moving object, or sometimes a stationary object? You probably figured I couldn't get through a whole lesson without some type of a space reference. So I want us to imagine that you're piloting a spacecraft to dock with the International Space Station. Both the spacecraft and the space station are orbiting Earth, but just because you're moving fast doesn't mean you're getting closer. The International Space Station is moving at about 28,000 kilometers an hour eastward around the Earth. Your spacecraft is moving 28,010 kilometers per hour eastward, just a little bit faster. From someone standing on Earth, both the ISS and your spacecraft are zooming around the planet at nearly 28,000 kilometers an hour, but from your point of view inside the spacecraft, your space station seems to be moving slowly backward because you're moving slightly faster than the space station. So this is this idea of relative velocity. And to find relative velocity of one object to another, if we are going to take the velocity of one to the other, and take the velocity of one minus the velocity of the other. So let's take a look at an example so you can see what we're talking about here. So here's our example. The velocities of a car, truck, and plane are 50 kilometers an hour east, 60 kilometers an hour west, and 200 kilometers an hour north, respectively. So let's draw those out so that we have an idea of what these look like. So I'm going to make the car red. So my car is heading east with a velocity of 50 kilometers per hour. I'm going to make the truck blue. The truck is moving west at 60 kilometers per hour. And let's make our airplane green. And the airplane is moving 200 kilometers an hour in the north direction. So this is my plane. This is my truck. And this is my car. So if I want to find the velocity of the car relative to the truck, what I want to consider here is the velocity of the car to the truck, and that's going to be equal to the velocity of the car minus the velocity of the truck. If you've ever driven on a highway, maybe not the 401, but a non-divided highway, if you're going 100 kilometers in one direction and a car is approaching you also going 100 kilometers an hour, when you pass each other, the other vehicle seems like it's going twice as fast. And that's what we're talking about when we're talking about relative velocity. So we're going to think about this as subtracting these vectors of this car and this truck approaching each other. But remember, to subtract a vector, we need to reverse its direction by making it negative. So we're subtracting a negative number. Or the other way you can think about it is the physics way of thinking about it in terms of direction. So if I'm setting east as positive, west will be negative. And so if I'm adding vectors, they have to be going in the same direction. They have to be relative to each other. So I have the velocity of the car relative to the truck. That's what I'm figuring out. Well, my car is going 50 kilometers an hour east. My truck is going 60 kilometers an hour, but it's going west. In order to do this math, I have to change this to be east. So the opposite of 60 kilometers west is going to be negative 60 kilometers east. Same as subtracting the vector, changing its direction. So now we have 50 plus 60. So the velocity of the car relative to the truck is going to be 110 kilometers per hour, and that is in the easterly direction. Now let's think about the car to the plane. We can think of it the same way. We can do the same kind of math if we want to do the car to the plane. So now we're going to do the velocity of the car to the plane. And the velocity of the car to the plane is going to be the velocity of the car minus the velocity of the plane. But you may have noticed that they are going in different directions. They're not on the same axes. They're not both east-west or north-south. One is going east and one is going north. So we're going to go ahead and do our math here anyway, and we're going to say that we have 50 kilometers an hour east, that's the car, minus my 200 kilometers an hour north. Remember, to add them, I need to add them tip to tail, which means I need to reverse this vector. So I need to reverse this one to make it go in the other direction, and that makes it a negative. Reversing a vector or changing its direction makes it negative. So that's minus 200. So that gives us 50 kilometers an hour east plus 200 kilometers an hour south. Remember, we reverse a vector, it changes its direction, it also changes its sign. Now, this just becomes a right-angled triangle problem. I can't just add them because they're in different one is going east and one is going south, but I can redraw this and make it just a triangle problem. So we have a magnitude of 50 kilometers an hour east. We have another vector here with a magnitude of 200 kilometers per hour south. And I want to find the resultant vector. Pythagorean theorem to get my magnitude. So velocity of the car relative to the plane is going to squared is going to be equal to 50 squared plus 200 squared. So my velocity of my car relative to the plane is going to be 206.16 kilometers per hour. Now we need to know the direction. To do that, I can use my tan. So tan, where can I put it? Let's make this a little bigger. Get my angle, tan theta is equal to my opposite over my adjacent, 200 over 50. So theta will be equal to 76 degrees. So we can say that the velocity of the car relative to the plane is equal to 206 kilometers per hour, and that will be east 76 degrees south. Okay, so those were just a few quick examples. Now what I'd like you to do is go ahead and take a look at the homework questions. There's quite a few there. If you feel like you're getting the hang of it, you certainly don't have to do all of them. If you have any questions, feel free to reach out.